let's talk snubbers or clamps, whatever you want to call them. This is not an active clamp. This is a very rudimentary, passive type snubber. And you can see we have a capacitor on the mains input here from our variable transformer. That solves a lot of issue right there with just having voltage ripple and things like that. Actually going into our transformer here, on the negative end we have a diode coming from the negative, current respective, into this 100 watt 20 ohm resistor, into another diode, back into the positive, going to the cell. We did have something else here previously, but it seems like just this one resistor with the diodes going from negative to positive to offer that power someplace to go really seems to do the trick. That is very hot though, so it might be more than 100 watts that's pushing through that. I may need a larger resistor, but at any rate, this capacitor and that one here, I'm going to disconnect this snubber right here and show you what the waveform looks like. This is what the waveform, pay attention to that purple here. We'll just we'll look at that for right now. Just that purple. As that voltage goes up, you can see 10 volts right there, 20, 30. You can see we have a pretty good flat line for that DC. We do have some ripple current in it and things like that. We can zoom in here and kind of see the spikes on it that way, but relatively low noise as far as that goes. That's all the way at 24 volts, so we're going to take that back down, pause it, and remove that snubber. Snubber is disconnected. We are going to turn this on and likely fry a MOSFET in the process, but we're going to see here as we power this on, see those spikes right there? Ooh, nasty, nasty spikes. This is only at 15 volts here too. If I turned it up too much higher, it will start to perhaps burn my MOSFET. You can see that really dirty snap action here. And as we increase that voltage higher, the spikes become louder and more dangerous. So, with that said, that snubber makes all the difference. Alright, snubber connected again. You can see here again we have those lines are much smaller here, so maybe a different resistor, more resistance would reduce this further, but for right now they're preventing my MOSFET from burning, so we are good to go. Next, I'm going to be disconnecting this capacitor here at our mains power supply. So here we go. That capacitor is disconnected here. I'm going to power on, and we're going to see all kinds of dirty noise. Look how terrible this is. I'm going to pause this and turn this off just to prevent damage to my MOSFET here, but we're going to zoom in just a little bit and just see all the disastrous noise here. The ringing and the pulse input time, off time, absolutely terrible. So literally, just by adding this capacitor to the main power input, that is before it reaches the MOSFET given, really cleans up our 12 volt to 30 volt rail from our adjustable power supply here, and prevents all types of bad things from happening from our MOSFET. So yeah, very key to have our snubber and our capacitor in place here to reduce that noise. Here, I'm gonna zoom in like that right there, pause it, and show you on the return. This is at about 15 volts, I think. There you go, with that capacitor back in place, you can see that ripple is much lower and very reasonable. And as we increase the voltage, that still stays within a tolerable amount, preventing me from frying the multitude of MOSFETs that I've fried in the past. Very crucial. We're going to look next into a different type of snubber, an active clamp, to see if we can push this efficiency higher and maybe even reduce the amperage consumption of the actual circuit itself. More to come.
This is Stan's Revenge.